Students, welcome to the next part of our chapter alternating current. Now we are discussing an important quantity which we found in the expression for average power, that is the power factor. We know that the average power is given by P average is equal to product of RMS value of voltage and current multiplied by another factor, that is cos phi, where phi is the phase angle between the voltage and the current for a given AC circuit. In this equation, cos phi term is known as the power factor. So when we write the average power as product of ERMS, IRMS and cos phi, this much term, the product of RMS value of the voltage and the current, we call it as the apparent power. When this apparent power is multiplied by the power factor, we get what we call as average power, or the actual power, or the true power consumed in the AC circuit. So unlike in the DC circuits where power is simply equal to the product of voltage and current, that will be the actual power consumed in the DC circuit. The same is not possible for the AC circuits, because for AC circuits, either inductive effects or capacitive effects present in the circuit, they are going to induce a certain value of the phase angle between the voltage and the current. So what is the actual power that is consumed by the AC circuit, that not only depends upon the RMS value of voltage and current, but it also depends upon the value of the phase angle. So in order to have very high value of the actual power consumed by the circuit, it is very essential to keep the value of the power factor, that is cos phi, also as high as possible. We know that maximum value of the cos phi is equal to plus 1 when phi is equal to 0, when the phase angle is equal to 0 degree. So in this case, in actual AC circuits, it is desirable to have phase angle as close as possible to 0, so that the value of power factor can lie close to unity. So in order to have very large value of actual power consumed in the AC circuits. So power factor we can define as the ratio of the true power and the apparent power, that is cos phi is equal to true power divided by the apparent power. Now cos phi from the impedance triangle can also be written as ratio of R over ohmic resistance and the impedance, that is it will be equal to R over R square plus XL minus XC whole square under the root. We know that for a pure inductive or a capacitive circuit, the phase angle is equal to pi by 2. So power factor cos pi by 2 become equal to 0. This means that average value of the power consumed for inductive or a capacitive circuit is also equal to 0. Whereas for a pure resistive circuit, phi is equal to 0, cos phi becomes equal to plus 1, which is the maximum value. So in that case, the average power consumed is ERMS and IRMS, which is the maximum power consumed in the ohmic circuit, in a resistive circuit. So actual power consumed in the AC circuits, no, it essentially depends upon the power factor value. So this power correction is very essential in the heavy machinery. Heavy machinery, they require high voltage and high value of the current to run. But if high currents are to be supplied to the machinery, we require thick cables in order to reduce the resistance. But if thick cables are required, the cost of installation of machinery, it is going to increase. So instead of using the high value of the thick cables for supplying current to the machinery, which can increase to the cost, the value of the power factor is adjusted so that without requiring thick cable, the heavy machinery can be operated. For this, what we do, the value of power factor is increased by decreasing the phase angle. For example, if the heavy machinery AC circuit is working as an inductive circuit, then it is going to have a phase angle of almost pi by 2 radian between the voltage and current. So in order to decrease the phase angle, what we do, we can attach a capacitor along with the AC circuit of the heavy machinery, because phase angle of inductor and capacitor both are pi by 2, but in inductor voltage is leading the current, and in capacitor current is leading the voltage. So both of voltage and current in case of inductor and capacitor, they are having a total phase angle of pi radian, pi by 2 plus pi by 2. So they are working opposite to each other. So when capacitor will be connected, it is going to cancel the inductive effect present in the heavy machinery, thereby reducing the value of the phase angle. So power factor can be increased. So when the value of the power factor increases, what happens, the current required, it decreases. We know that average power is equal to ERMS IRMS into cos phi. From here, RMS current will be equal to average power divided by ERMS into the power factor, that is cos phi. So here you can see that RMS current is inversely proportional to the cos phi power factor. So if power factor can be increased, so without requiring thick cable, we can decrease the value of the current running into the wires, and heavy machinery can be operated at the normal thickness cables. So this is what we call as the power correction in the heavy machinery. Next important thing we are discussing is the wattless component of current, or wattless current. We know that average power is ERMS into IRMS into the cos phi, where phi is the phase angle between the voltage and the current. Diagrammatically we can represent it like this. If along x-axis we have the RMS value of the current, and this is our RMS value of the voltage, and this is the phase angle between them. In this case, what we can do, we can decompose our RMS current into two rectangular components. So if this is our RMS current, from here we can drop a perpendicular on the voltage axis. So we will have a right angle triangle, say OMP. If we decompose our RMS current into two components, we will have one component IRMS cos phi in the direction of the virtual value of the voltage, and we will have one component perpendicular to the voltage, which will be IRMS into the sin phi. So whenever voltage and current, their RMS values in an AC circuit, they have phase angle phi in between them, then the current can be divided into two rectangular components, IRMS cos phi and IRMS sin phi. In this case, the first component is the component IRMS cos phi. This component is called as the wattful component of the current. We call this as wattful component of the current because actual wattage of the power that is consumed by the AC circuit, it arises because of this current IRMS cos phi current present in the circuit. From the figure it is clear that this component of current is directed in the direction of the virtual value of the voltage. So here the average power consumed by this particular current is given by ERMS into the component of the current, that is IRMS into cos phi, multiplied by cos of the phase angle between ERMS and IRMS cos phi. Both are inclined in same direction, so angle between them is 0. So it will be cos 0. So average power consumed will be ERMS into IRMS into cos phi. So this is the actual power or the true power consumed in the circuit. But if we look at the second component, IRMS sin phi, we call this as wattless component because it is not responsible for any useful work done in the AC circuit. From figure it is clear that this component is inclined at 90 degree with respect to the virtual value of the voltage. So power consumed for this component of current will be ERMS into IRMS sin phi into cos of the angle between ERMS and IRMS sin phi, which is pi by 2. Cos pi by 2 is 0, so average power consumed is equal to 0. So that's why we define this component as that for a current, if a average power consumed is 0, then that current is called as wattless current, or it is also called as the ideal current. Now we have already seen that in case of pure inductive or pure capacitive circuits, the phase angle between voltage and current is pi by 2, corresponding to which average power consumed is equal to 0. This means that the current which is flowing in pure inductive or pure capacitive circuits, it is wattless component of the current. There is no wattful component. Wattful component is actual current which is responsible for the actual power consumed for the circuit. For example, if a motor is running by AC motor is running by supplying some current to it, then actual electrical energy which is getting converted into the mechanical energy by the AC motor, that arises because of the wattful component of the current. But we know that there will also be some heating of the coils of the motor. That heat that is produced in the coils of the motor, that is because of this component of the current, which is wattless component of current. So wattful component is responsible for actual useful electrical energy. Wattless is responsible for the loss of energy. That's why in order to have minimum amount of this wattless component of the current, the phase angle between voltage and current should be kept as low as possible, so that the value of the wattless component of the current is almost near to the zero, in order to keep the energy loss as minimum as possible.